which need to be discussed. So I will just re-quote the central limit theorem again, and in that way we can make sure that we understand. So it said that essentially xn are basically all data sets from a random sample, and what we understand is that they are IID. Also, since they are IID, what we can do is we are also given that E of xi is basically mu, while variance of xi is sigma squared. ঠিক আছে, একটু B2 বিল্ডিং সেকেন্ড ফ্লোর বলে দেবেন, আমি না থাকলেও বাড়িতে লোক আছে, তুলবো। কে ফোন করবে? আপনি করবেন? ঠিক আছে, একদম তুলবো। এই নাম্বার দিয়ে ফোন আসবে? ঠিক আছে। So the variance is sigma square and the mean is mu, and what we can do with it is that we are given from this statement of the central limit theorem that limit n tends to infinity, probability divided by sigma by root n less than equals to t for some real number t is equals to phi z of t, where phi z is the standard normal CDF, right? So this is basically the statement. Now try to understand this for a moment, that how we can expand this. Try to think that how we can expand e to the power minus x square here. So from Taylor series expansion we do know that e to the power minus x square is n equals to 0 to infinity x square whole to the power n by n factorial. The prerequisite for Taylor series and this related integrations will also be embedded, so not to worry about that. Now after we have done that, we can use it inside the definition of standard normal CDF as follows. This should be x to the power 2n by n factorial dx, right? and this is how we work with it. Now what we can again do is we can write this as limit p tends to infinity 1 by root over of 2 pi summation of n equals to 0 to infinity minus p to t x to the power 2n. You can write the 1 by n factorial here dx, and this gives you limit p tends to infinity 1 by root over of 2 pi summation of n equals to 0 to infinity, and this thing becomes basically t to the power 2n plus 1 minus of minus p whole to the power 2n plus 1, but minus 1 whole to the power 2n plus 1 is again minus, so it is basically plus p to the power 2n plus 1. So this is basically the sum we are trying to evaluate. So all in all, what we can say is the standard normal CDF can be written as follows: phi z of t is simply 1 by root over of 2 pi limit p tends to infinity summation of n equals to 0 to infinity t to the power 2n plus 1 plus p to the power 2n plus 1 divided by n factorial into 2n plus 1. So you see that this kind of definitions make sure that we are no longer in position to define all the matrices and all the corresponding definitions, but well, we get an entire series representation for the phi z of t, and what we can do is we can approximate it well if we take the first 100 terms or for 1000 terms and stuff like that. So that is how basically the z scores are calculated, and also by numerical integration as well. So this is how we deal with this stuff. Now along with the central limit theorem, what we will also learn is the follow. So this will be learning again in the next one. This is law of large numbers. So law of large numbers is something we are going to do. So there are two versions like WLLN and SLLN, which means weak law of large numbers and strong law of large numbers, and we are going to study both of them. So attached will it be the series representations, the Taylor series, the integration prerequisite with this video as well, and in the next one we shall continue with WLLN and SLLN, and after that video we will try to do some problems on the central limit theorem and on the standard normal CDF as well, what we did in the last one. So we say that two random variables x and y are jointly distributed on the region A, which is basically a subset of R square. It can also be R square itself. Then we say that the double integral or the surface integral over the region A simply equals 1 of the joint PDF, right? Here fxy is the joint PDF. Okay. And in the last one we understood how to do this kind of manipulations. Now in this one, let us understand what are marginal PDFs first. So this is the joint PDF, marginal PDF for x. So what we are saying here is, if two random variables are jointly distributed with the joint PDF fxy x comma y, where xy belongs to the subset A, where A is a subset of R square, or it might be R square itself, then the marginal PDF for x is given by f of x equals to. So what you do is you take the joint PDF fxy and you integrate it with respect to the variable y. So if you are willing to find out the marginal PDF for x, what we are going to do is we are going to integrate over y. Similarly, so these are called the marginal PDFs. So let us find out the marginal PDF for the previous question. Now, to find out the marginal PDF for x, we need to integrate over y, right? So therefore, now this would become x plus 3 by 2 into 1 by 3, and this would become x plus half, right? So therefore the PDF of x is for x is f of x equals to x plus 1 by 2 0 less than equals to x less than equals to 1. Therefore, for y we can do for y we can do now we need to integrate over x, so it becomes minus infinity to plus infinity fxx dx, and this becomes 0 to 1 x plus 3 by 2 y squared dx, and this would become 1 by 2 plus 3 by 2 y squared, and this in turn would become 1 plus 3y squared by 2, and obviously this is the PDF for y, so therefore for y is this. And this would be how it is done. Now, well, this again requires methods of integration, which I have already attached at the end of the video, so you can watch them for the reference of this integrations. And obviously this would be a short timed one. For the next one we would do some 2 or 3 examples to make sure that we understand the problems. So up to this part we are clear because what we have said is this, and we understand what W is. W is basically a standard normal variable, a normal variable, a normal random variable with mean 0 and variance 1 by 9. Now, that brings question A. So I'll explain the problem again, but let me just write down the questions. There are five such questions. So the first one is write the null hypothesis. Write the null hypothesis and the alternate hypothesis in the terms of theta. So that completes the questions, and now let me explain how do we actually do it. So basically, it says that consider a radar system that uses radio waves to detect aircrafts. So there is a radar system that uses the radio waves and it detects aircrafts are present or not. So this how it works is the system first receives a signal, and based on the received signal, it needs to decide whether there is an aircraft present or not. Right now, if X is the received signal, and we already know that if X is W, then there is no aircraft present, and if X is 1 plus W, then there is an aircraft present. Right now, here W is just W belongs is basically a normal random variable with mean 0 and variance 1 upon 9. So that's the probability distribution of W. So W takes values according to which has probabilities according to a normal distribution with mean 0 and value variance 1 by 9. Thus, what we can do is we can write x equals to theta plus W. We're just trying to introduce a parameter, and you would notice that if theta is 0, then x is basically W, which means there is no aircraft present, and if theta is 1, it means there is an aircraft present, and we can write x is 1 and 1 plus W. Now suppose that we define the null hypothesis H naught as no aircraft is present, while the alternative hypothesis H1 as an aircraft is present. Now the questions. Let's go for number 1. Write the null hypothesis and the alternative hypothesis in terms of theta, right? So the simple hypotheses are as follows. Part A, we have that H naught, which is the null hypothesis, it can be written as theta equals to 0. That is, no aircraft is present. Then we have H1. H1 is basically the alternative hypothesis. So let me write down alternative, and this is theta equals to 1. That is, aircraft is present. Okay. Now to decide between H0 and H1, we look at the observed data, obviously, and this observed data tells us if we can differentiate between H0 and H1. That completes part 1. Let's now for B, design a level 0.05 test to decide between H0 and H1. So when we say a 0.05 test, what we actually mean is we are trying to decide, we are trying to make a test which can help us distinguish if to decide between what is true, H0 or H1, what to accept and what to reject, and the level of significance should be 0.05, which should be our helping hand. So to decide between H1 and H0 and H1, we look at the observed data. The observed data is just the random variable x, right? The observed data random variable x under H naught x follows normal distribution with mean 0 and variance 1 by 9. And under h1 what happens? So this is under h0, right? And under h1 what happens is it follows normal distribution with mean 1 and variance 1 by 9. Why is it so? I'll explain that. Because under h0 w, therefore e of x is equals to e of w, and w is a standard normal variable with mean 0. So this is this, and also variance of x should just be variance of w, which is 1 by 9. Therefore x also follows a normal distribution with mean 0 and variance 1 by n. And under h1 x is 1 plus w, and this means e of x is simply so the mean is 1, and adding a constant to the variable doesn't change its variance, because variance of x then would be variance of 1 plus w, therefore x follows normal distribution with mean 1 and variance 1 by 9. So yeah, that's how it works. Now the test. Now what we are saying here is we can suggest the following test where we choose a threshold c, and if the observed value of x is less than c, we can choose h0. Otherwise, if it is larger than c, we can choose h1. So that's what we are going to do. Now to choose that c, we are going to use our required alpha. So let's see. Probability of tripe error is basically reject h0. Was we made sure that the probability portion got into multiple random variables and stuff like that. Now our entire goal of this was to study higher probability and statistics, which we shall begin. And for that we need to know the basic to intermediate portions of statistics and how all those probabilistic criteria and solutions would actually work in a real life scenario, right? So I'll just write it down and let us see. So what we are doing is we are beginning a bit of statistics here. So in statistics we deal about something called data. When I say data, what I mean is we have clusters of points which represents some identity or some information about a certain quantity, and we would like to investigate about those data points or those cluster of points, and we would like to find certain information about it. For example, what we can do is we can measure heights of certain people. So let's say we have 10 people, and what we do is we measure heights for each of them. What we can do is we can name the heights measured as x1, x2, and all the way up to x10. Let this be the data points. Okay, so what are these? These are the data for our sample experiment or whatever we're going to do. Now using this data, what we can do is entirely a different subject, because there are a lot of things we can try on this data, but for the basics, for the sake of basic statistics, what we can do is we can find the mean, the mode, the median, we can find the skewness, the kurtosis. Also we can see if they fit into any probability distribution, and moreover what we can do is we can find probabilities of certain heights being improbable or certain heights being like very likely, right? And maybe there are more than 10 people, maybe there are like 1000 people, and we did a random sampling of those 1000 people, and we selected 10 people at random, and then we selected the heights, and from this heights what we need to do is we need to give a general idea about what would happen to the heights of the other people, or you can say the height of the population, which is of the 1000 people. Can we get an idea about the height of the population from the height from the data points secured in this sample? That is the ultimate question. That is, let us say we were trying to investigate some statistics about the whole country, and there are a lot of people in the country, right? So let's say there are 100 crore people right now, for example, and what we want to do, we cannot sample 100 crore people, that would take a lot of time, and that is why we are being realistic here. We are not really being mathematical, because in mathematics we can even sample 10 to the power 100 people, right, with in a finite number of years, but that doesn't make sense. So let us say we can sample 1 lakh people or 100,000 people, and we would like to get an idea about the whole population from the sample of this 100 lakh people, 100,000 people. And what we would like to do is we would like to select them randomly and uniformly from the population, so that no selection is biased, every selection is uniform, and every selection is equally likely. When we do that, the question is, can we get the idea about the whole population? Ideas like what is the average height of the population, ideas like what is the height that goes on the furthest, above which range do we have a 20% chance of getting a certain height, and stuff like that. So we shall begin with something called mean. So what is the mean? Let me write it down. Right. Similarly, the median. So if this is the mean, the median is given by and after we are done sorting the data in ascending order, what we need to see is the middle points. Now since there are an even number of them, there are two middle points, that is x5 and x6, and they contribute to the median m, which is given by the average of this two. Okay, and if it not were even, let us say we had 5 quantities, then there is only one middle number, that is the third one, so we only take that one, right? So it makes sense, because what we understand from this kind of criteria is that we need to be clinical about our data set, and there are a lot of things we can do with the data, and it's usually a good idea to sort them into ascending order before doing any calculations, because it helps us figure out how the data is increasing. We can also graph the data. So this mean, this median, whatever we're talking about, these are called statistics. So statistics are basically a function of the data points. So an example of a statistics would be, so covariance of x comma y would be e of xy minus e of x into e of y, right? Where e of y is defined as integral over all r y into f of y dy, and e of xy on the other hand is basically a double integral where fxy x comma y is the joint distribution of x and y. So this provides the way to make sure that we have our expectations correct, and obviously integration is very much required in each of probability and statistics courses, because integration and derivative, they form the base of calculus, and in each step we shall find ourselves to be doing some kind of integration or differentiation, right? So that is one way. Now let us see what we can do with some of the things we have here. Let us begin with a topic here. So what is point estimation again? So we have talked about it before in probability, but let us talk about it in detail here. What is point estimation? Suppose we have B, a point estimator, for a parameter theta. Now what we do know is bias of a estimator is as follows. So bias of an estimator is given by expected value of the estimator minus the estimator. You see, so that is how bias is defined, and we call it unbiased if bias is 0. So we call so if this happens, we call our estimator unbiased, right? Now we can take an example to see that why this is the case and how we can prove such questions. So let us take a small example. So that is the question in we need to show, not of itself, obviously it's unbiased estimator of theta equals to exi. The parameter is theta, which is equals to e of xi for every I, right? So how do we show that? We see that e of this phi cap is basically e so now we use the properties of expectation as follows. Therefore we see that e of phi cap is basically equals to theta, which means it's a phi cap is an unbiased estimator of theta, and that is why it is basically unbiased, and our problem is solved. Now this is how we solve this problems, and showing that something is an unbiased estimator specifically involves finding the expectation of the point estimator, and this expectation may well involved some kind of integration or summation, which we have discussed before, I think, and those are required. Now after this, what we will learn is the mean squared error. So this is the mean squared error, because phi cap minus theta is the error that we make when we are going to estimate theta based on phi cap. Because see, phi cap is an estimator of theta, right? But since we say estimator, we are not really guaranteed that phi cap would always equal to theta. So it estimates theta, so there can be some error, and that error is given by phi cap minus theta. And mean squared error is basically we square the error first, which is phi cap minus theta squared, and then we take the mean of it. And in statistics and probability, when we say mean, we always mean the expected value, because the parameters and everything else, they can be a continuous random variable or a discrete random variable kind of thing, and we need to do integration or summation over that, right? So that is one way. Also, what we can find out from this is, so the MSC is basically the equal to variance of the estimator plus bias of the estimator squared. This is another way to find out that. Now, here comes an important property of showing something is a consistent estimator. So our topic is how to show how to show if some estimator is consistent, right? To do that, what we can do is we say minus theta is greater than equal to epsilon, and this is equals to 0, of course, for all epsilon greater than 0. So this is basically the definition for the epsilon delta case and stuff like that. And we can make sure that this works. So let us do one example for that. Suppose x1 x2 all the way up to xn be a random sample with mean e of xi equals to theta and variance of xi equals to sigma square. Okay, we need to show that is an consistent estimator of theta. And obviously we first do the integral definitions of this. We want to say that this is, since let fxx be the common PDF, then exi is simply fx dx, while variance of xi is x minus exi squared fxx dx. Okay, and we want to show that theta n is a consistent estimator, where theta n is basically equals to the sample mean. So given and we would like to show that this is the consistent estimator of exi, and let exi be equals to theta, which is also given. So therefore we need to show the following. So then probability that theta n cap minus theta absolute value is greater than equal to epsilon is equal to, so what we do see here is that they have a common PDF and they would like to, they can be treated as equals, right? Now this means that what we can do is we can use the Chebyshev's inequality here, because we see that E of theta n cap is E of 1 by n summation of I equals to 1 to n xi, which is 1 by n and this becomes theta, right? Therefore using Chebyshev's inequality we have less than equals to variance of theta n by epsilon square, and now variance of theta n is basically variance of x bar by epsilon square. Now what is variance of x bar? Variance of x bar is simply equal to and this would be 1. So since the alternative hypothesis is simple, which means that basically when you are going to do the alternative hypothesis, we see that there is exactly one value included in it, that is theta equals to 1, which means it's a simple hypothesis, and thus the probability of type 2 error is basically accepting h naught when h1 is true, right? So when do we accept h naught? We know that we accept h naught when x is less than c, right? And given h1, but under h1 x is 1 plus w, so it can be written as 1 plus w less than c, right? Now This means the probability of W less than C minus 1. And we can write this as Z less than 3 into C minus 1, where Z is a standard normal variable, and this amounts again to the CDF 3 of C minus 1. And now, since C is 0.548, we have beta equals to 0. Not 588, it's basically 088, which completes our part B, right? So for part D, we see if we observe x equals to 0.6, is there enough evidence to reject h naught at the level 0.01? Okay, let's do that. Since we have already obtained this previously, we can use right, but here x equals to 0.6, which is less than c. Thus, we cannot we cannot reject h naught at alpha equals to 0.01 if x equals to 0.6. So there is not enough evidence to reject that. Okay. Now we come to the last part, which is part E. If we would like the probability of the missing an aircraft to be less than 5.1, right? Less than what? Less than 5%. Sorry. Yeah. What is the smallest significance level we can achieve? Okay. So now what we want is we want beta equals to 0.05, right? Then and this gives you 0.452, right? Thus, what we understand is we need to have c is less than or equals to 0.452 to obtain this. Now we see that the smallest significance level we can achieve with this is, and now since significance level is the same as type 1 error, we can see this is equals to phi of 3c, and this is less than equals to 1 minus phi of 3 times 0.452, which equals 0.0875. So the smallest right. Okay, so this is another problem, and let us do another one. This one would be from the section of IBP. So obviously whenever you're facing or you're in a situation where you are in exam or some problem solving session, you might not be given the topic, right? So you might have to figure out on your own how to do a certain problem of integration, if it's a definite integral or even if it's an indefinite integral. You might have to substitute for something, you might have to do integration by parts. So there are various ways to do an integral, and you need to figure out which way works for you, which way actually solves the integral, because other ways might actually make you go round and round and come back to the same integrand again, right? So let us evaluate x sin x dx, and after that we'll do a more complicated version of this. So denote by I the integral, and whenever we see functions which are product of two different kinds of functions, we try to remember our eyelet rule, where we obviously know which one to take first function and which one to take second function. So in the eyelet rule, as you can see, eyelet, the algebraic function comes first after the trigonometric function. So algebraic function should be part 1, function 1, and the trigonometric one should be function 2, right? Then we have I equals to x into integral of sin x dx minus derivative of x, which is d dx of x, into integral of sin x dx, and whole thing is dx here, right? Now integral of sin x is minus cos x, so this is minus x cos x dx, minus x cos x, minus d dx of x is just 1, and integral of sin x is again minus cos x, right? Then as you can see, it simplifies considerably into minus x cos x, and this minus make it a plus, and 1 into cos x is cos x dx, and you do know the integral for cos x dx, which is just sin x, right? So the answer is x minus x cos x plus sin x plus c. So this integral is something which just comes back around its own, because the trigonometric functions, the sin x and cos x functions, generally they come back around its own when you integrate them enough number of times. So for example, they have a period of 4 on integration. So if you integrate sin x 4 times, you will actually get the same result. So let us try to find out something else here. Next problem would be integral of e to the power x sin x dx. Now this is a problem where you would know why the denote by integral I is of paramount importance. Okay, let's see. Denote the integral by I. Then what we have is I is equal to e to the power x sin x dx. Now if you remember in the rule eyelet, e, that is for exponential functions, that came last. So obviously e to the power x is going to be the second function here, and sin x is going to be the first function. So applying IBP, or applying integration by parts, what we have is this: I is equals to sin x into integral of e to the power x dx minus d dx of sin x into integral of e to the power x dx dx, right? So what we do get is integral of e to the power x is just e to the power x, so it becomes e to the power x sin x, minus differentiation of sin x is cos x, so cos x into e to the power x dx. Now this is another integral. So again we apply the same integration by parts technique with cos x as the first function and e to the power x as the second function. Notice how we have to do integration by parts twice here, and we are doing it, as you will see why. It becomes cos of x into integration of e to the power x dx minus the integration of ddx of cos x, and as you know, integration of e to the power x dx is just e to the power x. I'll just write e to the power x dx here. So it becomes e to the power x sin x minus e to the power x cos x, and ddx of cos x is minus sin x, and minus becomes plus. It becomes e to the power x sin x dx. And if you take it away from the bracket, what becomes is e to the power x sin x minus e to the power x cos x minus integral of e to the power x sin x dx. But notice that this is the integral that we started with, right? So this is denoted by I, which is a variable. So this becomes e to the power x sin x minus e to the power x cos x minus I, and on the left hand side we have I. So solving for I, what we get, solving for I, we get 2i equals to e to the power x sin x minus e to the power x cos x. Therefore I is equal to e to the power x whole into sin x minus cos x by 2, which obviously there is a plus c, which is the answer. So this is one of those integrals where you have to do integration by parts twice to get the answer. So this is a problem where we have basically the integral coming back on its own, and then we have to solve it like that. So this happens a lot of times. So let us do another problem. This one would be a bit tad harder than the last one because of the concepts involved. Evaluate integral of sine of log x plus cos of log x dx, right? Now obviously what we want to do here is, first, as this is not any function that we can be reminded of, this is not any elementary function, neither does it have substitution that is very clearly visible. So obviously the derivative of log x is also not present, right? So naturally the first thing we would like to try is to substitute for log x and see if that makes any difference, right? So obviously I is equals to integration of sine of log x plus cosine of log x dx, and substitute y equals to log x, which will give us dy equals to 1 by x dx, right? Therefore this integral would become, and from this you can see that dx is basically equal to dy into x, but we need it in terms of y, so x is basically e to the power y, so dx is basically e to the power y dy, right? So the integral becomes sine of y plus cos of y whole into e to the power y dy. And this is time to introduce a new theorem, or rather a lemma, which is helpful sometimes. So lemma: for a differentiable function f of x, if I is equal to integral of e to the power x into f of x plus f dash x dx, then the integral is I equals to e to the power x into fx plus c. So if you have an integral in this form, the answer is simply e to the power x into f of x. So the proof is necessary, so we shall do the proof here. We start with the integral. Given integral, and we shall see why this lemma is important in solving this problem, this particular problem. So given integral is I equals to e to the power x whole into f of x plus f dash x dx. Now let us separate it into two different parts, that is e to the power x into f of x dx plus e to the power x into f prime of x, or derivative of fx dx. So let us try to break down this second integral. Name this integral as b. So b equals to integral of e to the power x into f prime x dx. If you apply integration by parts here with e to the power x as the first function and f dash x as the second function, what you do get is e to the power x into f dash x dx minus derivative of e to the power x is just e to the power x and integral of e to the f dash x and then a dx outside, right? Now we know that the integral of a derivative is just the function itself, so it just becomes e to the power x into f of x minus this becomes integral of e to the power x into f of x dx, right? So if we put the value of b there, we see that I is equals to integral of e to the power x f of x dx plus b, where b is our desired integral which we have just evaluated using integration by parts, and which becomes e to the power x into f of x dx plus e to the power x into f of x minus integral of e to the power x into f of x dx. And as you can see, these two integrals cut off because they are exactly the same thing. So the answer is just e to the power x into f of x, which is the answer for the integral. Now in our given problem, in our given problem, we have I equals to integral of e to the power y, it was, into sine y plus cos y, right? So let f of y equals to sine of y, then f dashed y would be equals to cosine of y, and therefore I equals to e to the power y into f of y, which is sine of y, and cos y is the derivative, so f dashed y, right? And from the lemma we see that this is basically equals to e to the power y into f of y plus c. Putting back y, we get e to the power, and what was y again? Y was log of x, right? So we get e to the power ln x into f of ln x plus c. Now e to the power ln x is just x and f of ln x is just sine of ln x plus c, which is the answer to our integral.